This is problem 633. It's on page 347. We're trying to find the centroid of the combined shape here. We're also trying to find the second moment of area through the centroid, assuming we have a horizontal axis. Notice it's made up of four pieces. There's a plate at the bottom, a plate at the top. Those are just simple rectangles. And then there's a couple of L-shaped brackets that are standard shapes. How do we use the spreadsheet in this case? Well, there are a couple of different ways we could approach this. One way would be to approximate the L-shaped brackets as a couple of rectangles. That would be valid. Another way would be to use data from the back of the book, from the appendix, that says if you've got this particular shape, here are the area properties, and it includes all the details of the radii and so forth. Let's see what I did. I don't actually recall. Let's find out. So let's see. I started off with a total area of 6 to make it easy to figure out, or to remember, or to understand what's being done. I multiplied it out. So it's pretty simple. This is the top plate, 1/2 inch by 12 inches. Okay, so there's the area. That makes sense. I always measure from the very bottom of the shape. So the centroid of that top plate would be up at 4 3/4 inches minus half the thickness, so that's minus 1/4, so that's 4 1/2 inches. So my yi for that upper plate is 4 1/2 inches. And then the product of those two is the first aiyi term for this plane, or this plate. It's basically the moment of that area about a line going through the very bottom horizontally of that shape. Next, what did I do? Well, the 2.5, that's 10 times 1/4, so that's the bottom plate. Okay, not really a surprise. I mean, its height is pretty small. Its height is 0.125. So the height is from the bottom line up, well, half of a 1/4 of an inch is an eighth, and that's 0.125. So that's where that number comes from. There's our aiyi. What about these two? Notice there are two of them. Well, it doesn't matter that one bracket is one way and the other bracket's the other way, that they're right and left hands of one another. The way that the area is distributed against that bottom line at the bottom of this combined shape is the same regardless. And so what I did here is I looked up the area properties for L 4 by 3 by 1/4 steel. And these are angles. You should go to the back of your book now and find it. I don't have a page number for you, but it is in the back of your book. And you can find the area that each one of these has in cross section. Apparently it's 1.69 square inches. And you can also find the location of the centroid. Now the centroid of these L's is weighted down towards this end because of that arm, but it's still up, here somewhere. I don't remember where. 1.47 inches. Now I had to be careful here. Notice what I did. What I did is I added 1/4 inch to 1.22. Now the 1.22 is the number that I got from the back of the book. And maybe it's measured from the other end. I don't think so. I think on L's it's measured from this face here. It's of course measured from this back face as well over, but that's not the dimension I'm interested in. You got to be careful and get the right dimension. Notice the longer leg is up. Okay, so 1.22 inches from this line, from the line between the 1/4 inch plate and the bottom, the foot of the L, up to the centroid of the L itself is 1.22 inches, so I had to add the thickness of the 1/4 inch plate to it to get the position of the centroid of the L reference to the bottom line, okay, the very bottom of that overall combined shape. And then here's the aiyi, and so we just, as usual, add all the aiyi's, add all the total area, divide the two by one another, and that tells us the height of the centroid of the overall shape, the area, right? So measuring from the very bottom of the 1/4 inch plate up, the centroid's at 2.72 inches or so up. Now the moment of inertia for the upper plate is pretty straightforward. It's just a rectangle, BH cubed over 12. You've seen this several times by now. Same thing with the bottom plate. It's just a thin plate, so we don't get much from it. It's not a surprise that's very low. What about these? Where did these come from? Well, these came from the back of the book. When I looked up the area properties of these angles, this was the number, 2.7 inches to the fourth power. Be really careful about your units. You have to know what units you're working in. The second moment of area has units of inches or length to the fourth power. You can tell that by looking at, 1/12 bh cubed. The 12 in the denominator doesn't have any units, but the 12 in the numerator here is 12 inches wide. It's that upper plate. And the half is a half inch. So 12 inches times a half inch cubed, well, that's inches times inches cubed. That's inches to the fourth power. And so these better be inches to the fourth power as well. They are if you look them up. Now the centroid location of all the areas I've listed, so we can calculate the distance between the location of the centroid of the overall area and each individual area. That's what's being done here. Doesn't matter that it's negative, because then we're going to take each area, multiply it by the square of that distance, and then that's the modifier for the moment of inertia through the individual centroids, so that we get the moment of inertia of all of these through the centroid of the combined shape. Notice the thing that adds the most inertia is this upper plate. Okay, it adds about half of the total inertia. But this thin quarter-inch plate is this thin quarter-inch plate is also pretty important, right? Look at that number, 16. That's almost the other half, not quite, maybe a third or so. And then the two L brackets do provide some moment of inertia. I like to think of this as stiffness, because that's what it really is. It's a geometric stiffness for beams. So the reason we're studying all this stuff is because we're going to use these area properties later on when we're working with beams.